Hello guys, welcome to our chemistry discussions. Today we are going to have a discussion on the November 2023 paper, chemistry, paper 3. So this is advanced level, A-level chemistry. So we have begun our massive topical revisions in preparation for the exams. So if you are doing Cambridge or any other examples, you need to engage in our discussions. Here we don't stick to examples, but we try to have many questions from different examples so that we can broaden our foundation, we can broaden our understanding in the principles of chemistry. So if you're doing Zimsec, you need to understand these instructions to candidates. So in this paper, you are required to answer 6 questions, and then you are required to answer 2 from section A, which is the physical section, and then 1 from section B, which is the inorganic, and then 2 from the section C, which is the organic, and then lastly we have section D, the options, right? So we are now diving into the first part of the question, and I hope you guys have done this paper already before watching this video, so that you can make use of this session to assess yourself, right? So for section A, number 1 says the isotopes of copper and their relative abundance is shown. The isotopes of copper and their relative abundance is shown in the table. So we've got the first isotope with isotopic mass of 68, and then the next isotope with the isotopic mass of 64, and then we are given this abundance, right? So the first part requires us to define the term relative isotopic mass. So here we don't mainly stick to the given question, but we try to expand the questions in relation to any of the concept within that given radius, so that we can broaden our foundation. We can have an understanding in our multiple choice paper, our structured paper, our free response, even the practical paper, right? So we need to define the term isotope. So isotopes, these are defined as atoms of the same element with the same number of protons, same number of electrons, but different number of neutrons. So these subatomic particles, you've got the same protons, same electrons, but different number of neutrons, meaning to say different mass numbers. So the mass number is made up of the proton plus the neutron. So if we are having different number of neutrons, it simply means that we are going to have different mass numbers. So isotopes, you've got the same proton, same number of electrons, same number of protons, but different number of neutrons. You need to take note of that one, and also you should be able to define the term allotrope. So allotropes are defined as atoms of the same element with different arrangement in the lattice structure. Same element but different arrangement in the lattice structure. So that's the definition for allotropes. So examples of allotropes, we've got carbon and graphite. These are more common examples of allotropes. We also have oxygen and ozone. You need to take note of that one, right? So we have got graphene, we've got Buckminster fluorescence. These are other examples of allotropes for carbon, but graphite and carbon are the more common ones, right? So you need to know the difference between the uses of graphite and carbon, graphite and diamond, right? You need to know the uses between graphite and diamond, because the different in arrangement of particles will result in different physical properties, thereby having different physical properties. Since physical properties are governed by the arrangement of particles, what we call the lattice structure. So diamond exhibits a giant molecular lattice structure whereby the bonds are held by the strong covalent bonds, and then graphite exhibits a hexagonal two-dimensional lattice structure which is layered, and we've got sp2 hybridized orbitals in graphite, and then sp3 in diamond. So you need to take note of the differences between graphite and diamond, right? So here we are given abundance, which is defined as the percentage occurrence of the isotope in the natural occurring element, right? So you should know the definition of each and every term within that topic, right? So we are given abundance and isotopic mass. So we are required to define the term relative atomic mass. So atomic mass, relative atomic mass, relative isotopic mass is defined as the average mass of an isotope of an element measured relative to 1/12 mass of a carbon 12 atom, right? The average mass of an isotope measured relative to 1/12 mass of a carbon 12 atom, right? So you should know the definition of relative atomic mass, relative isotopic mass, relative formula mass, relative molecular mass, the more the Avogadro's law, right? So you should know the difference between relative formula mass and relative molecular mass. So you should know the difference. Here we're using formula units. So using formula units, and then here we're using molecules, right? So this one is for covalent compounds, and then this one is for ionic compounds. So you should know the difference between the two. A relative formula mass is defined as the average mass of the formula units found in a ionic compound measured relative to 1/12 mass of a carbon 12 atom. And then relative molecular mass is defined as the average mass of a molecule measured relative to 1/12 mass of a carbon 12 atom. So that is the definition you need to be aware of, right? And then we're now moving on to the next part, which says calculate the relative atomic mass of copper. So we use the formula. So AR is equal to isotopic mass multiplied by abundance plus isotopic mass of the next isotope multiplied by abundance. So this is the formula over total abundance. So we are simply going to the given information. So the isotopic mass here is 68 and the abundance is equal to 7. So abundance can be in the form of percentage. So you need to take note of that one, right? And then we are given 65 and 3. So it's 65 by 3 over total abundance, which is equal to 10. 7 by plus 3. So we're going straight to our calculator. So it's 68 by 7 to give us 476, and then 65 by 3 to give us 195 all over 10. So it's 476 plus 195 divided by 10. So we're going to have 67.1. So this is the relative atomic mass, right? So you should also explain how the mass spectrometer works. So it is one of the most frequently examined questions. Describe how a mass spectrometer works, right? So you should know how the mass spectrometer works. And then the next part says define. Let me clear this one. So we are required to define the term lattice enthalpy. So it can be also called lattice energy, right? So lattice enthalpy is defined as the energy released or the energy evolved when one mole of a solid ionic compound is formed from its gaseous ions under standard conditions, right? So it is the energy evolved when one mole of a solid ionic compound is formed from its gaseous ions and under standard conditions. So you should also state the standard conditions of 1 atm and a temperature of 298 kelvins. So these are the standard conditions. So here in the definition, you need to take note of this solid ionic compound. So we are going to form a solid ionic compound, right? One more. Also take note of this one more. These are the key terms you need to take note of when describing the standard enthalpy change of lattice energy, right? So it is the heat evolved, not the heat change. So meaning to say it is always exothermic. It is always exothermic, right? So we're going to move on to the next part of the question, which says state and explain state and explain two factors that affect the magnitude of lattice enthalpy. So lattice enthalpy, from the definition, we understand that it is the energy released, meaning to say it is always exothermic when one mole of a solid ionic compound, so meaning to say we are having a positively charged ion, which is the cation, and the negatively charged ion, which is the anion. So the energy released when these two bond, it is what we call the lattice energy or lattice enthalpy. So the smaller, so it is governed by two factors: ionic size and ionic charge. So the smaller the ions, the bigger the electrostatic force of attraction between the ions, and then the bigger the charges, the bigger the electrostatic force of attraction between the particles, thereby leading to a stronger or a larger magnitude of enthalpy, right? So you can say that smaller ions allow closer approach, thereby enhancing. So that's enhancing the electrostatic forces of attraction between the particles or between the ions, thereby resulting in a larger magnitude of lattice enthalpy, right? And then we can also say that the higher the charges or the bigger the charges, the stronger the lattice enthalpy, or the bigger the magnitude of lattice enthalpy. So higher charges on the ions, increases the strength, to increase the strength of the electrostatic forces of attraction between the oppositely charged ions, thereby increasing the magnitude of lattice energy or lattice enthalpy, right? So we're now moving on to the next part, which says explain why the enthalpy change of hydration of magnesium is equal to 1927, whilst that one of sodium is equal to 406. So enthalpy change of hydration is always negative, meaning to say it is always an exothermic reaction. It is being evolved. So it is defined as the heat evolved when one mole of a gaseous ion completely dissolve in water to form an infinitely dilute solution under standard conditions of 1 atm and 298 kelvins. So we are having magnesium having a higher enthalpy of hydration, and then sodium ion having a lower. So enthalpy change of hydration is governed by what we call the charge density. So charge density, we are saying that we are having this magnesium ion with a smaller radii than the sodium ion. So across the period ionic radii decreases. So again, you have this for inorganic. So this one is for anions, and this one is for cations, right? So across the period we are having this sodium ion, and then this one magnesium ion. So the smaller the ion, the bigger the effective nuclear charge on the exterior environment, right? So effective nuclear charge is more experienced on these magnesium ions compared to this sodium ion. And then we are having a charge of +2, and then you are having a charge of +1, meaning to say we are going to have strong attractions here than here. So this +1 singly charged ion is being distributed over a larger region, and then this +2 is being distributed over a smaller region, meaning to say it is more experienced in this exterior exterior environment. And then from the definition, we are having water molecules. So water molecules are has got a negative region. So this is our oxygen, and then this one is our hydrogen. And then water has got the oxygen atom has got 2 lone pairs. So these magnesium ions will have a strong attraction to this negative electron sender, the electron region, than this sodium ion. So the attractions here are smaller compared to the attractions of this magnesium ion. Why? Because of this charge density ratio, because of the smaller ionic size. So we can explain our answer saying that the more the negative value of magnesium ion compared to that one of sodium is due to the high charge density, right? High charge density of magnesium ion. You have a smaller ionic radius, right, than the sodium ion. So the ionic radius of magnesium is smaller than that one of sodium, and we also have a higher charge of +2 on magnesium, and then +1 on sodium. So the charge density of magnesium, the charge density of magnesium is higher than sodium ion. So this will result in the stronger ion to dipole interactions with the water molecule, right? With the water molecule, thereby releasing more energy, right? So this is the explanation why the enthalpy change of hydration is larger for magnesium than that one of sodium, because of charge density ratio, which will then allow the strong ion dipole moments or ion dipole interaction between the water molecules and the magnesium ion. So I hope this is clear, and we are now moving on to the next part. So the next part of the question says, state 2 conditions for the formation of hydrogen bonding. So hydrogen bonding, we are having hydrogen bonded directly to one of the most electronegative atoms, which possesses a lone pair of electrons. So hydrogen must be bonded directly to one of the most electronegativity atoms. Must be bonded directly, and then the electronegative atom, must have at least one lone pair of electrons. So examples for these atoms, we are going to have a fluorine, nitrogen, and then oxygen, right? So these are the electronegative atoms, right? And then we are moving on to the next part. So the next part says, sketch a PV against P on the XM axis to show the following gases, how they deviate from ideal behavior. So you've got ammonia, carbon dioxide, and then helium. So let me add another page so that we can control the graph clearly, right? So it's PV. So this is my PV against P. So this is my horizontal axis. And then here we are having the ideal gas. So this one is the ideal gas. And then noble gases, they deviate slightly from ideal behavior. So here is my helium. Right, so let me rub. Must deviate slightly. So this is my helium. And then carbon dioxide will deviate. Right, and then ammonia will deviate mostly from ideal behavior. So here we are having ammonia, and then here we are having carbon dioxide, and then here helium. So here is the ideal gas behavior. So this is the graph PV against P. We're moving on to the next part, which says explain the difference in the graph. So helium doesn't deviate as much as other gases from the ideality because it is a noble gas. So noble gases exist as mono atomic particles, right? So the forces or the van der Waals forces between the particles are weak as compared to other compounds. So for every noble gases, the group 8 elements, the noble gases, they have got they exhibit a simple molecular lattice structure where the monoatomic particles are held by the weak van der Waals forces. So the monoatomic particles are held by the weak van der Waals forces. And then we move on to carbon dioxide, which exhibits a simple lattice structure, simple molecular lattice structure, where the particles are held by the stronger. So here we've got stronger van der Waals forces compared to that one of helium. For helium we've got weak, and then here we've got stronger van der Waals forces, thereby increasing the strength of the lattice structure. So this will cause the molecule to deviate more from ideality nature, right? So carbon dioxide will deviate more from ideality. And then in ammonia, right? So in ammonia, hydrogen is bonded directly to one of the more electronegative atom. So this one we are going to have hydrogen bonding. So here we've got van der Waals forces, and then here we are going to have the hydrogen bonding. So hydrogen bonding is the strongest, one of the strongest intermolecular forces. So thereby increasing the strength within the lattice structure of the molecule, thereby causing the molecule to deviate much from ideality. So we can say that in helium, so there is a simple molecular lattice structure whereby the monoatomic particles are held by the weak van der Waals forces. And then for carbon dioxide, the van der Waals same lattice structure, simple molecular lattice structure whereby the particles are held by the weak van der Waals forces. But the van der Waals forces in carbon dioxide are much stronger than those in the small monatomic particles in the helium. So you have got weak van der Waals forces, and then you have got stronger van der Waals forces, causing carbon dioxide to deviate more from behavior. And then for ammonia, we have a simple molecular lattice structure, but with different forces. Here we've got hydrogen bonds as the intermolecular forces, thereby increasing the strength of the molecule, thereby causing it to deviate much from ideal behavior. So that is what you need to know for your explanation. So we are now moving on to the next part, of the question, which is number 2. So number 2 says, define the term rate determining step. So this is reaction kinetics, right? So rate determining step is defined as the slowest step in a reaction mechanism which determines the overall rate of a reaction. So it is the slowest step in a reaction mechanism which determines which determines the overall rate of a reaction. So this is the definition, and we also have to define the term order of a reaction. Order of a reaction is defined as the power to which the concentration of a reactant is raised to in a rate equation. So these are appropriate powers to which the concentration of a reactant is raised to in a rate equation. And then the reaction shown is a second order reaction with respect to nitrogen monoxide, and a zero order reaction with respect to carbon monoxide and oxygen. So this is the equation, right? And then we are required to sketch the curve to show how the rate of a reaction changes with respect to nitrogen monoxide and oxygen. So we are told that this one is second order, and then this one is a zero order. It is zero order with respect to the reaction, right? So zero order, we are saying that, so zero order, the rate law is only dependent on the rate constant, right? So the reaction is independent to the reactant. So rate is independent of the concentration of the reactant, right? And then for the first order, we can say that first order, the rate of reaction is directly proportional to the concentration of the reactant. So we have got this equation. So this shows that it is directly proportional to the concentration of the reactant A. When we also have a constant half-life. So half-life for first order, it is constant. So that half-life is constant here. And then we go on to second order reaction. Second order reaction. So the rate of the reaction is proportional to the square of the concentration of the reactant. Is proportional to the square of the concentration of A. So we can say that rate is proportional to the concentration of A squared. So rate is equal to K A squared. So this is for second order, right? So we are required to draw. To sketch a curve, right? So the curve, you can sketch the curve in this form. So we can have rate on the vertical axis, and then the concentration of reactant, right, on this. So this one is for zero order, right? And then zero order, the rate is independent of this reactant, right? And then for second order, this one is for second order, which is nitrogen monoxide, second order. And then for first order, it is direct proportional. So this one first order, and then this one zero, and then this one second, right? So you should take note of these sketches, right? So we are now moving on to the next part. So we says at temperature at X degrees, the rate constant is 1.76 times 10 to the power 3 moles per cubic decimeters per second. And then at Y degrees, the rate constant is 5.8 times 10 to the power 3 moles per cubic decimeter per second. Deduce with a reason whether Y is at a lower or at a higher temperature. So the rate at Y is bigger than the rate at X. So meaning to say Y is at higher temperature, right? So Y is at higher temperature. Why? Because the rate is higher at Y than at X. So the rate constants increases with increasing rate constants increase with increase in temperature. So this is because the molecular kinetic energy of the particles increases, leading to more frequent collisions and more energetic collision that will overcome the activation energy. So that's why the rate increases, right? So that's why the rate constant increases. So at Y the temperature is high due to the rate constant increases, the increase in temperature due to increase in kinetic energy of the molecules, and then leading to more energetic and more frequent collisions that overcome the activation energy, which is the minimum amount of energy required to start a chemical reaction, right? So we are now moving on to the next to part number B. So part number B says write an equation to show how phosphoric acid reacts with water. So phosphoric acids react with water, so according to this equation, so it's H3PO4 plus water to give the hydronium ion plus, so this is the equation. So we are having this equation, right, is required by the question. So this one is a strong acid, is fully ionized in water, and then identify the conjugate acid base pairs in the solution. So the conjugate acid base pairs in the equation 1. So we have phosphoric acid as the acid, and then so this one is the conjugate base, right? And then is the conjugate base, and then we have H2O is the base, the proton acceptor, and then hydronium ion is the acid, conjugate acid, the proton donor, right? So we've done is required by the question. And then the next part says predict the shape and the bond angles of the two product species in the equation, right? So the products, we have the hydronium ion. So the shape, the hydronium ion is H3O3 plus. So water, oxygen is the central atom, and then bonded to one hydrogen atom, and then this proton, a dative bond. So this proton comes to the reaction being donated by the acid, and it doesn't have any electrons, so there's dative bond here, and then lone pairs of electrons here. So 3 bonding pairs and 1 lone pair. We are going to have a trigonal pyramidal shape of bond angle 107 degrees. So it's trigonal pyramidal. So this is the shape. So we can draw the shape in this way, H, and then H here, and then indicate the lone pair, right? So this is the bond angle with 107 degrees. And then for this ion, so it's H2PO4 minus. So we must identify the central atom, which is phosphorus, bonded to 4 oxygen atoms. So we have 1 oxygen atom, and then we have 1 oxygen atom, and then we have another oxygen atom. So this oxygen atom is bonded to hydrogen, and then this one to hydrogen. So let me highlight the bonds. So we've bonded to hydrogen. So we've used all the hydrogen atoms, right? And then this one, 2 bonds, and then we are left with 1 oxygen atom. So we have this negative charge, which indicates that one of the oxygen atom is coming to the reaction with already 7 electrons, 1 from the system, right? So we have a single bond here, and then this electron from the system is indicated by a triangle, right? So this is the shape of the molecule, and then we have a bond angle of about, so we can draw it obeying the Vesper theorem, that the bond angles will repel themselves and arrange themselves in such a way which will minimize repulsions. So you can draw it in this way. Let me rub this one. So it's P, and then double bond, and then O with this electron, and then we have this oxygen atom, and then this oxygen atom, and then bonded this hydrogen, and then this hydrogen atom, and then we have this bond angle. So for bonding pairs, we have 109.5 degrees, which is the tetrahedral shape. So this is the shape of this molecule, right? And then we are moving on to the next part of the question. So number C says, during electrolysis of dilute sodium sulfate connected in series with silver nitrate, a current of 2 amps was passed, and then a mass of 25 grams of silver were deposited. So connected in series, meaning to say you have same charge, right? And then we have deposited silver, right? And then the part 1 says, calculate the time required to deposit silver. So silver is deposited by this equation: silver ion plus electron to give silver metal. So this equation is balanced, and we have 1 electron. So we have got this formula which says M is equal to mR multiplied by I multiplied by T all over N multiplied by F, right? So mR is the molecular mass, and then I is the current, and then T is equal to the time in seconds, and then N the number of electrons, and then F the Faraday's constant, which is equal to 96,500 coulombs per mole. And then we are simply going to make T the subject of the formula, because we are being required to calculate the time required to deposit 25 grams, right? So to make T the subject of the formula is M multiplied by N multiplied by F all over mR multiplied by I, the current, is equal to T. So we are simply substituting. So our M, the mass, is equal to 25 multiplied by N. So here we've got 1 electron, and then multiplied by F, which is 96,500, and then divided by mR. So the mR of silver from the periodic table, we've got 108 multiplied by the current, which is equal to 2 amps, right? So we have 2 amps. So we're simply going to punch this on our calculator. So it's 25 multiplied by 96,500 divided by 108 multiplied by 2, and we are going to have 11,168.98 seconds to 2 decimal places, right? And then we move on to the next part. So the next part of the question says, calculate the volume of gas produced at the anode in the sodium sulfate cell, right? So for sodium sulfate, dilute sodium sulfate, so it's dilute. We have the cations, we have the sodium ion and the proton, and then for anions we have got the sulfate ion and the hydroxide ion. So this one is at the anode, which is being discharged. It is less stable, and then the sulfate ion is more stable compared to this one. So we are going to discharge the hydroxide ion. So hydroxide ion is being, so for at the anode we have oxidation, and then at the cathode we have a reduction. So the hydroxide ion is oxidized to oxygen and water. So we can balance this equation by having, so oxidation, the loss of electrons, right? So we can balance by 2 here, and then by 4 here, and then 4 electrons here. So for every 4 moles of electrons, we are also having 1 mole of oxygen gas. So you need to take note on this ratio. So we can use the formula Q for charge is equal to IT. So we want to find the charge which is being used, right? So we are sharing the same current, right? So charge is equal to, current is equal to 2 amps multiplied by T, time, which is 11,168.998 seconds, right? So we are going straight to our calculator to multiply to multiply 2 by 11, 168.98, right? So we're going to have current is 22337996. So this is the current, this is the charge for 4 moles of electrons, right? So for 4 moles of electrons, so we know that from the Faraday's constant that the charge of 1 mole is equal to 96. The charge of 1 mole of electrons is equal to 9650. So we want to find the amount of moles within this given charge, for this given charge, right? So less is equal to 22337.96. So the number of moles is 1 mole. Number of moles of electrons is equal to 1 mole, 22337.96 over 96500. So we're going straight to our calculator to divide with 96500 to give us 0.23148,145 number of moles of electrons. So we know from this equation that for every 1 mole of oxygen we are having 4 moles of electrons. So 1 mole of oxygen is equal to 4 moles of electrons. So less is equal to this number of moles of electrons. So less is equal to 0.3148145. So we're going to carry simple proportion. We're going to divide by 4 and find the number of moles of oxygen produced. So we are having 0.57870,362. So 1 mole, so we are told that it is at RTP, right? So this is at RTP, right? So 1 mole of any gas at RTP is equal to 24 cubic decimeters. So less is being produced when we have 0.057870362, right? So we are going to have 0.05257870362 multiplied by 24 cubic decimeters. Multiplied by 24 cubic decimeters. So we are going to have 1.38888. It's a recurring number. So to 2 decimal places, we're going to have 1.39 cubic decimeters of oxygen. So we move on to the next part of the question, which says explain why the lead acid accumulator becomes flat after a period of discharge. Explain why the lead acid accumulator becomes flat after a period of discharge. So the lead acid accumulator is the battery which we use in car batteries, and it becomes flat after a period of discharge because of the chemical changes that occurs during the discharge processes. So during discharging, we have so let me clear this so that we can easily simplify our explanations, right? So during discharging at the anode, that's where oxidation takes place. At the anode, we have lead P-beam plus the sulfate ion from sulfuric acid. So sulfuric acid is the electrolyte to give lead 2 sulfate plus 2 electrons. And then at the cathode, we have lead 2 oxide. So it's P-beam plus lead 2 oxide plus the sulfuric acid to give lead 2 sulfate plus water, right? So to balance this equation, we are going to have a 2 here and a 2 here, and also a 2 for water. So this equation is now balanced. So this is the equation for the cathode, and then this one is for the anode. So as you can see that during this process, there is formation of lead 2 sulfate by both the anode and the cathode reaction. They are both producing lead 2 sulfate. So the formation of lead 2 sulfate, which is insoluble, will reduce the effectiveness of the battery. So the continuous production of lead 2 sulfate at both electrodes. So this one is insoluble, right? will reduce the effectiveness of the battery. And also take note that the concentration of the electrolyte sulfuric acid decreases with time, right? The concentration of the electrolyte sulfuric acid decreases with time. So you need to take note that the main reason or the major reason why the battery stops, why the battery becomes flat, is due to the production of lead-2 sulfate and the decrease in concentration of sulfuric acid. So lead-2 sulfate also causes build-up of internal resistance, which reduces the current output. So this causes the increase in resistance, which reduce current output. So we are done, and now we are now moving on to the next part, which is number 3. So number 3 says, state the Lee-Chatelius principle. So we are required to state the Lee-Chatelius principle. So the Lee-Chatelius principle states that if a system in equilibrium is disturbed, the equilibrium position will shift to oppose the change and try to restore a new equilibrium, right? So if the system in equilibrium is disturbed, the equilibrium system will shift to oppose or to counteract the change and try to restore a new equilibrium, right? So this is the simple definition for the Lee-Chatelius principle. So you should know the Lee-Chatelius principle by heart, because it is the one which governs all the reactions, all the predictions we are going to make in the equilibrium series, right? So number B says water exists in equilibrium with its ions as shown below. So we've got water, and then the hydroxide ion, and then the proton. So this is the ionic product of water, the dissociation equation, right? So we are told that the enthalpy change of reaction is plus 58 kilojoules per mole, meaning to say it is an endothermic reaction. And then the first part says state and explain the effect on the position of equilibrium of. So part 1 says increasing temperature, and then part 2 says adding hydrochloric acid, right? So we are going to have this equation, water dissociating to give the proton plus the hydroxide ion in aqueous, and then here in aqueous phase. So this whole equation, the forward reaction, it is endothermic in nature, right? So this forward reaction is endothermic in nature. So this forward is endothermic, and then this one is exothermic in nature. So if you were to increase temperature, here, we will favor this forward reaction, so that we are going to have a cooling effect to maintain the temperature, right? The original temperature. So we said that the Lee-Chatelius principle states that if a disturbance is added, the equilibrium position will shift in the opposite direction of the disturbance and try to maintain the equilibrium position, right? So if we are to increase temperature here, we are going to shift this, the equilibrium position is going to shift to this forward reaction, trying to cool the increased temperature, right? Since this forward reaction has got a cooling effect. So our answer is going to say that increase in temperature, the increase in temperature will favor the forward reaction to absorb the added heat or temperature, thereby the equilibrium position will shift to the right. The equilibrium equilibrium position. We will shift to the right, increasing the concentration of the proton and hydroxide ion. And then the next part says adding hydrochloric acid. So hydrochloric acid is a strong acid which fully dissociates to give the proton and the chloride ion, right? It fully dissociates. It fully to give the proton plus the chloride ion, right? So we have aqueous hydrochloric acid. So if we were to add hydrochloric acid, in other words, we're increasing the concentration of the hydrogen ion and the concentration of the chloride ion. So adding to this equation the concentration of hydrogen ion, we are increasing here, right? So the equilibrium position will shift into this direction, which will reduce this the concentration of the proton, right? Increase the concentration of the proton. So when we increase hydrochloric acid, we are adding more protons here, thereby forcing the equilibrium position to shift to the left, so to the backward. So we are promoting the backward reaction. So in our explanation, we can say that adding hydrochloric acid will dissociate according to this equation. So according to Le Chatelier's principle, the system will shift to the left to reduce the added proton, right? Thereby favoring the backward reaction. So if you are dealing with these reversible reactions, what you should stick to is the Le Chatelier's principle, right? You should stick to the Le Chatelier's principle, right? So we are done on this part. So we are now moving on to the next part. So the next part says write the expression for the equilibrium constant Kw and state the units. So the equilibrium constant for Kw, so Kw is equal to the concentration of proton multiplied by the concentration of the hydroxide ion. So we are simply saying moles per cubic decimeters for the proton multiplied by moles per cubic decimeters for the hydroxide ion. So this will give us mole squared cubic decimeter to the power 6, right? So this is the these are the units for the constant, right? So the next part, the next equation says explain why the value of the ionic product of water Kw is affected by changes in temperature, not by changes in concentration. So this one is a tricky question, but you need to pay attention. So the changes in concentration will shift the position of equilibrium, but does not affect the Kw. It will shift the position of equilibrium proportionally. The way it shifts the reactants is proportional to the way it shifts the products. So meaning to say the value of Kw doesn't change. But if you are to increase temperature, if you are to change either to increase or to decrease temperature, we are going to affect one reaction dominantly. So we are going to either affect the forward reaction dominantly or to affect the backward reaction dominantly, thereby affecting the value of Kw. So you should take note of that one. And then we are now moving on to number C. So number C says when iodic acid with this formula is dissolved in water, it ionizes slightly according to the equation to the following equilibrium. So we have got this equation, and then in a 0.5 moles per cubic decimeter solution of iodic acid, the concentration of hydrogen ions at equilibrium was found to be 0.22. Calculate the equilibrium concentration of the acid and then find Ka, the acid dissociation constant. So we'll simply clear this so that we can have more space. So we have this equation, right? And then the proton, and then the conjugate base, right? So at equilibrium, we're going to have 1 minus x, and then here we're going to have x, and then here we're going to have x. And then we are told that at equilibrium we've got 0.22 moles of the proton. So we are going to have 0.22 here. So x is equal to 0.22, meaning to say x is equal to 0.22 here, right? And then 1 minus x, so 1 is the initial concentration of the acid. So we are going to have 0.5 minus x, which is equal to 0.22. So this is the concentration at equilibrium, right? So at equilibrium we have this concentration, right, at equilibrium. And then we're going to use our calculator. 0.5 minus 0.22, we're going to get 0.28, and then 0.22 here, 0.22 here. And then we've answered the first part, so the concentration is going to 0.28, this one, right? And then find the acid dissociation constant Ka. So Ka is equal to the concentration of the proton over the concentration of the acid at equilibrium. So we're going to simply substitute the values. So the proton we have 0.22, and then for the conjugate space we have 0.22 again. So you need to take note of the units. So here the units are moles per cubic decimeters, and then times 2, so meaning to say we are going to square. And then the concentration of the acid, so here we need to put the units moles per cubic decimeters, right? So take note on that one. So we are going to have 0.28 moles per cubic decimeters, right? So this one will cancel with this 2, right? And then we simply punch this on the calculator and maintain the units. So Ka is equal to moles per cubic decimeters. So we're going to simply punch this on the calculator. 0.22 multiplied by 0.22 divided by 0.28, and this will give us 0.1723 SM, right? So this is the answer. So we are now moving on to section B.